So, this course, Energy, Resources and Technology, essentially will deal with the fundamentals of energy conversion, will deal with the conventional sources of energy, will deal with the non-conventional sources of energy. But initially, we will have to talk about the basics on which the whole edifice of energy engineering stands. And the basics stand on the ground of the laws of thermodynamics. Some of you may have done some courses on thermodynamics, some of you may not have. So, I guess I need to start from the basics. But in doing so, let me tell you that not only those who have done a course on thermodynamics, but even the people who have done research on thermodynamics, done path-breaking contributions in thermodynamics, all of them are very uncomfortable about this subject. Why? The basic reason is that all other laws of nature, all our other theories, rules that we have discovered in physics, they have all been discovered in order to explain something that happens in nature. You observe something, and in order to explain that, you propose a law, a rule, a theory. Take the Newton's law, you observe something, the fall of the apple from the hand or the motion of the moon, whatever it is, but some observation to explain which you needed a law. Then take for example the Maxwell's equations. You had the observational basis, Faraday's observations, Ampere's observation, Coulomb's observation about the relationship between the electricity and magnetism, and in order to explain that you had a set of laws. But the reason the thermodynamics laws are very uncomfortable, especially the second law, is that it was not discovered that way. It was not discovered by observing something and trying to explain it. It was discovered in trying to explain away a failure. What is it? By the way, before we go to the second law, do you remember what the first law was? First law of thermodynamics? Just the law of energy conservation. Energy can neither be created nor be destroyed. So, that of course was of the first category. That means you did observe that happening. So, if you for example spend mechanical energy and found that is converted into heat, then people tested how much was the mechanical energy, how much was the heat obtained, and they found that equal. So, in order to generalize that, the law was proposed, fine. But the second law was very peculiar in the sense that that was not proposed that way. So, what failure? You see, it has been the dream of man for ever since eternity to devise some kind of perpetual motion machine. That means something that will work all by itself. At the advent of the industrial revolution, when people found that you do need coal in order to run the industries, then people started the attempt to try to find out some way by which you can obtain motion without really spending anything, perpetual motion machine. And a huge amount of effort was spent, like about 100 years people kept on trying and trying and trying. To give you some examples, early 18th century there was a patent filed in the there was a patent was filed in the French patent office that said that the inventor had devised a way of obtaining a perpetual motion of a ship going in the sea. His idea was that there is a large amount of water around the ship. So, he said that what I will do is simply suck in water by means of something from the outside, and cool down the water by just 1 degree. And he calculated that if you suck in a reasonable amount of water and simply by cooling it by 1 degree, you get sufficient amount of heat in order to propel it through the sea from one continent to another. Do you see any problem with that? The patent application was rejected, by the way. So, do you see any problem with that? It really didn't work. Probably you understand why, right? There was only one temperature. You need two in order to generate, but that came later. I'll come to that later. So the point is that when people kept on trying and trying and trying for more than 100 years to devise a perpetual motion machine and failed, then people say that okay, it may be true that there exists a law of nature that prevents us from doing that. So let's state it as a law of nature, that it's impossible to make a perpetual motion machine. So that essentially is the starting point of the second law of thermodynamics. There is another reason for which scientists are somewhat uncomfortable about the second law of thermodynamics. That is, all other laws of physics are time reversible. What does it mean? It means that the Newton's law, the Maxwell's law, makes no distinction between the positive direction of time and the negative direction of time. If you substitute in a Newtonian equation, in place of t you put minus t, it will be perfectly the same, perfectly all right, perfectly logical and sensible equation. If you want to visualize what exactly I am meaning by that they don't distinguish between the positive and negative directions of time, Feynman had a nice way of visualizing that. You know, you heard of Feynman, right? Richard Feynman. He was an excellent scientist, excellent teacher, and he devised a nice way of visualizing what we mean by the positive and negative directions of time. He said that okay, suppose you have got a video camera like that one that is filming me, and you film an event and then run it in reverse. If you see something wrong happening, then obviously in that event there is some kind of arrow of time, some positive direction of time. But if you feel, if you by seeing it being run in reverse, if you cannot distinguish between the whether it's right or wrong, then obviously there is no direction of time involved in it. Imagine, suppose I have got a ball in hand and I drop it, and suppose it falls, and imagine that this is a perfect elastic material so that it rises to the same height. Perfect Newtonian collision and goes up. And suppose you film that event and run it in reverse. What do you see? Same thing, no difference really. So that tells you that the typical Newtonian mechanics has no distinction between the positive direction and negative direction of time. Imagine that in this room there are a huge number of molecules, right? And imagine the way the Gulliver's Travels were written. The person becomes small enough to become Lilliput. Imagine you have become a Lilliput, not only of the size of an inch, but of the size of a molecule. And you are inside this room. What will you see happening around you? You will see molecules coming, colliding, going away again, so all around you. And imagine that event you are holding a very, very tiny camera and you are filming and running it in reverse. Will you be able to see any difference? No. In that, you will not even be able to talk about any meaning of time. Time has a meaning only when the two things, the positive way of running it in the video and the negative way, the opposite way, has some distinction. Then only time has a meaning. Else time even doesn't have a meaning. Time doesn't have an arrow. So you see, there are by all the other laws of physics, the time does not have an arrow. time does not have a direction. There is no distinction between past and the future. But actually there is, right? Actually there is the distinction between the past and the future. How do we figure it out that there is a distinction between the past and the future? Again, takes recourse to Feynman's visualization and do that on any natural event. Say you have gone to our Harris shop and you have ordered a cup of tea. The fellow comes with a cup of tea, but imagine that just before he places it on your table, he tips and the cup falls from his hand. Something that happens, right? And suppose you have taken a video camera and pictured that event, and after coming home you have run it in reverse. What will you see? You see these splattered splinters of the cup on the floor with the tea on the floor all over, and all that will come together, and the splinters will again sum up into the whole cup, and the whole thing will fly up on your hand, right? It even makes this fellow smile. Means that the direction of time, the arrow of time is ingrained in our sense of humor, which is right. Many of the things that you see in nature are of that type. There is a arrow of time ingrained in it. But this is a very natural event, right? Imagine another event. Suppose a child has gone to the seashore in Puri or Digha or someplace like that, and he builds a sandcastle. Most of the children do. And then at the end of the day, his parents takes him away. So what happens to the sandcastle? Slowly, by the action of nature, by the action of the waves, it will be again the same sandy beach, right? Now if you film that process and run it in reverse, what will you see? A castle spontaneously rising from the sand, right? Something that never happens. So there also there is some kind of a arrow of time ingrained. Imagine a third event. Suppose there is a cylinder and a cylinder with gases, and there is a partition in between, and in the left side there is only oxygen, and the right side there is only nitrogen. And imagine the left hand side to facilitate the visualization, imagine the oxygen molecules are red in color and the nitrogen molecules are blue in color. So these two different types of molecules. Now suppose you run a video camera and remove the partition. What will you see? They will slowly mix. Come back home and run it in reverse. What will you see? That a perfect mixture looking violet will slowly separate out into two parts, red and blue. Something that never happens in nature. Okay. So you see, if you actually do this procedure on things that happen around you, you will find that there is a direction of time. But all the laws of physics says that the time is perfectly reversible. So there is something wrong. Something additional is needed. That additional thing is the second law of thermodynamics. So let's try to figure out what actually happened in all these cases. Now, in all these cases, take the case of the sandcastle, take the case of the cup in the waiter's hand. When the cup is in the waiter's hand, it had some order in it, right? The whole cup, the tea in it, and then when it fell, it became disorderly. The situation of you are not allowed to come in, you are not allowed to come in. So the cup that had a typical order in it, and when it fell, the order was lost. You had the situation of the sandcastle. The sandcastle has a shape, a size, an order. Due to the action of nature, that became disorderly. the cylinder with gases, when they were separated, that had some order. When they were mixed, the order became disorderly. So, intuitively that gives the idea, I mean I will later propose it as a law, but intuitively it is not difficult to visualize that by the spontaneous action of nature, order is going towards disorder, right, in all these cases. Never the opposite is happening, and that is exactly why you are seeing the past different from the future. Okay. So, can we then state it as a law that nature has a spontaneous tendency to lose order? It naturally goes from orderly state to disorderly state. In a natural process, that is the way it goes. There are pointers, I will come to that a little later, but there is another aspect to it. When the cup was whole with the tea in it, it contained information, right. You could measure the radius of the cup, the diameter of the cup, the shape of the structure, the strength, these are all informations. You could measure and say that this cup is defined by 1, 2, 3, 4, 5, 6, so many numbers. So, that contains information. When it broke, obviously that information is lost, right. When the sandcastle was there, it had some height, some width, some structure, and naturally it had contained information. And when it became again the sandy beach, the information was lost, right. In the case of the cylinder, of course, there was information contained in the situation where the two sides had different constituents, in the sense that you could say that if I am looking for an oxygen molecule, I can only look on the left hand side. If I am looking for a nitrogen molecule, I can only look on the right hand side. That contains information, right, these statements. So, we can also then make the statement that nature has a natural tendency of losing information, okay. Has a natural tendency of losing information. In general, these things are stated in a rather scientific way, not in the verbal manner in which I am stating. A scientist will say that a closed system, if left to itself, a closed system is something that has no interaction with the surroundings. A closed system, if left to itself, will spontaneously lose its orderliness, will spontaneously lose its information. Okay. So, these are the way, these are, remember, these are also alternative statements of the second law of thermodynamics. You can easily state that I will state the second law of thermodynamics simply by saying that for a closed system, there will be a spontaneous loss of information, that is it. That is perfectly valid statement of the second law of thermodynamics. Now, these are verbal statements, and in science we need to deal with numbers. So, when we say orderliness, we would like to quantify that. When we say disorderliness, we would like to quantify that. Now, how to quantify orderliness? How to quantify disorderliness? How to quantify how much information a thing contains? Now, I am saying something rather serious. Suppose there is something, and there are a huge number of ways in which that particular arrangement can be made. Say, these two pens, I can keep them this way, I can keep them this way, I can keep them this way, many possible ways. So, I can keep them this way, this way, this way, this way. Now, if I keep it this particular way, then out of many possibilities, I am making a choice, right, and that choice contains information in it. So, if we are to approach the question of quantifying orderliness, we will need to talk about out of various ways of arranging a particular thing, what is the probability of having a particular structure. Notice the statement I am making. Okay, let me clarify that in terms of the cylinder. The cylinder with two partitions, with one partition with two compartments. This compartment containing oxygen, that compartment containing nitrogen. What is the probability of this state? How will you approach this problem? You will say that suppose I have one molecule, it could be in this side, it could be in that side. What is the probability of finding it in the left hand side? Half, 1/2. I have another molecule. What is the probability of that being in the left half? Again half. I have another oxygen molecule. What is the probability of that being in the left half? Again half. So what is the probability of all three being in the left hand side? That is, what if the probability of one to be in the left hand side is half, what is the probability of two to be in the left hand side? Half square. Law of the multiplication of the probabilities. What is the probability of the third one to be also in the left half? Half cube. So if there are 1 million molecules, what is the probability? 1 million oxygen molecules. What is the probability of all of them to be in the left half? Half to the power million. Okay. So that half to the power million should be quantifying its probability of that whole status. Okay. So there are 1 million oxygen molecules, 1 million nitrogen molecules. What is the probability of this to happen? Is like half to the power million. That's a very small number. That's a very small number. That is exactly what says that it is a very orderly state. If it is mixed, then what is the probability? 1. We see it has to be in the whole. You cannot say whether it is left hand side or right hand side, it has to be in the whole. So you have the situation that while divided, it is a very, very low probability, while mixed up, it has a high probability. Okay. So the lower the probability of that particular state, the more information it carries, the more orderly the state is, right? So when we say that it went from orderliness to disorderliness, it actually went from a very low probability state to a high probability state. Can you make the statement? Okay. Still now, we need to quantify that. So what did we say? We said that the probability of one oxygen molecule to be in the left side was half. The probability of a second one to be in the left hand side was half to the power 2, and for 1 million molecule to be in the left hand side was, say, I will have to put something like 1 0 0 0 0 0 0. Is that a million? Yes. Okay. This is a very large number. Oh, sorry, very small number. This is a very small number. So small that you cannot enter in a calculator. So if I give you a problem to solve in the examination, to use this number, will you be able to use it? No. So something needs to be done to it. Huh? Something needs to be done to this number in order to make it handleable. What is the natural thing to be done? Take a logarithm. Take a logarithm. This fellow comes forward and it is no longer all that small a number. Huh? So this is the whole probability. This is the probability P. So in order to make it handleable, say we will say ln P, in which case this fellow comes forward and half remains. So it is more or less a handleable number, but still it is not very handleable, in the sense that 1 million molecule is not the right kind of number. In a cylinder there are far larger numbers. So it is still a very large number, difficult to handle. So what we do is we multiply it by a constant which is a very, very small number, so that the whole thing is a handleable quantity. And this K is the Boltzmann constant. K So, it is a very small number, very small number, which when multiplied with this you get a more or less handleable quantity. This is called the entropy. Okay. So, entropy is something that quantifies the orderly or disorderliness of a system. It is a concept that is related to the probability of a state. If something can be arranged in various possible ways, what is the probability of a particular state? You answer that question, obtain the probability, take the logarithm, and then multiply it by the Boltzmann constant, you get the entropy. So, that is the concept of entropy. Naturally, the entropy is related to the probability, is related to the orderliness. So, can you relate these two? So, for the prosaic concept of the orderliness and the numerical concept of the probability, the more disorderly a system, the higher the entropy. The more orderly a system, the lower the entropy. And therefore, the second law of thermodynamics can then be molded in the language of the entropy, where we will say if left to itself, that is it. All right. And this is what gives the arrow of time. This statement essentially tells us why is there an arrow of time, why is there a distinction between the past and the future. Essentially, this is the basic. So, we have actually made three statements of the second law. The first statement said that if left to itself, a closed system always loses its orderliness and goes towards disorderliness. We said that if left to itself, a closed system tends to lose its information, and we said by quantifying it that if left to itself, a closed system's entropy always increases. That is very fine. That is very fine. But then we do have orderly structures around us. If this is all true, then obviously the natural conclusion would be there should not be an orderly structure. How do we then survive? We do survive. A plant grows, for example, from a seed to a whole plant. As it grows, you can see that information is being created, right? It produces leaves that have specific structure, that have specific composition. So, these are information out of material that were earlier somewhat dispersed, disorderly. So, the opposite also happens. So, natural question should be that if, sir, you say this is true, this is the law, then how can that happen? Yes, that can happen only in an open system. A plant is an open system. It is not a closed system. Open system in the sense that it interacts with the environment and thereby it somehow manages to reduce its entropy. Okay. That somehow I will come to little later. But that is true for all living organisms. One of the characteristics of all living organisms is that they are open systems, and unless they are open systems, they can't survive. If you say enclose somebody in a coffin and live just like that, you will die. The entropy will increase, and the whole thing after some time you will find a disorderly mass. So, the only way living systems can survive is by, now this is a new concept, by sucking in orderliness from the environment. Whatever the in the whole disorderly mass that were around that was around it, the plant, for example, that sucks in whatever small amount of orderliness that was there around it and discharges some material in a disorderly form. So, it sucks in orderliness and discharges material in the disorderly form. That is what we also do, right? We eat, we breathe. So, we get material from outside by being a closed open system, and we also discharge. And there is a qualitative difference between what we take in and what we discharge, in the sense that what we take in has more orderliness than what we discharge. And by doing that, we maintain our orderliness. So, a system can maintain its orderliness by, now notice the term, by sucking in negentropy from the environment. So, I am introducing a term, negentropy. What does it mean? It means that normally if something is disorderly and within that some bit of orderliness is there, some concentration of some material is there, that in that sense sort of represents a pocket of orderliness. A pocket of orderliness. You can survive only by sucking in that pocket of orderliness from the environment and releasing material in a disorderly state. Okay. So, that is the only way we can survive. That is the only way the society can also survive. Society is an orderly thing. Notice that in order to survive, the society takes in whatever was the amount of negentropy that was there in the environment and discharges material in a very disorderly state, and the society can also survive by doing that. So, the point is that the society survives on negentropy stock. Whatever small amount of orderliness is there in our environment, the Earth's environment, the society survives only by sucking in that, utilizing that, and then discharging the material in a disorderly state. Let us come back to the question of the seashore and the child. You had a situation where the child built a sandcastle, left it, and it was ravished to the ground by the action of the sea. Can't the child come the next day and build it again? Yes. So, it is possible to reverse the action of nature, right? The cylinder with oxygen and nitrogen that had oxygen this side, nitrogen this side, you had opened the cylinder partition and then it got mixed up. Can't we separate it out? Yes, we can. By industrial process by which oxygen and nitrogen are made, we can always separate it out. The cup that fell from the waiter's hand, supposing it did not break, can't we pick it up and put it there? Yes, we can. If it broke, then also it is possible, at least in theory, to put it back again. Can't we do that? So, even though the law of entropy says that nature has an inherent tendency of going from orderliness to disorderliness, we do reverse that process, right? It is possible to reverse that process. How? What actually happens in terms of basic science when the child goes and builds it again? He spends energy, right? What actually happens when you separate the oxygen and nitrogen? You have to spend energy. What actually happens when the waiter picks up the cup? he spends energy. So, energy has to be spent in order to reverse that process. Energy has to be spent in order to reverse that process. It is possible to reverse the process, but that is possible only by spending energy. Naturally, when the society has to survive, the society has to build its industries, its houses, its clocks, its computers, everything. These are all very, very orderly things, very, very orderly structures. They contain a lot of information. And in order to produce that out of the things that we have in nature, you have to spend energy. So, that is the essential role of energy. So, what is the essential role of energy? To reverse the process that would naturally occur unless there is some intervention. And we intervene by using energy. The only way we can intervene in that process, in that natural process, is by using energy. That is why energy is so very important in the whole societal process. Without energy, the society cannot survive. So, is that point clear? Now, this negentropy, let us clarify what it is. When you talk about the sapling growing and it is sucking in negentropy from the environment, what exactly is the negentropy stock? It is those macromolecules that are there in the soil. Okay? That is what it is sucking in. And the macromolecules constitute the relatively more orderly structure than the mass of the material that is around it. And the sapling survives by sucking in those. We survive by eating vegetables, meat and stuff like that. Those are for us the sources of negentropy through which we survive. What is the source of negentropy for the society? As I said, the society can survive only by sucking in, utilizing the negentropy stock that is around it. So, what is the negentropy stock? See, the earth, had it been a completely homogeneous mixture of the constituent things that are there, like what is there in the earth? The earth contains silicates, that means silicon, oxygen and stuff, iron, nickel, cobalt and stuff like that, manganese, things like that. Now, if all these were very homogeneously mixed in the earth, do you think we will be able to make anything? No. So, the negentropy stock is in the common mass of the disorderly mass. If there is a pocket of concentration of any of these, like the iron ore, the manganese ore, these are the pockets of concentration of the one of these things. So, that then is the negentropy stock. That is the negentropy stock. So, the negentropy stock is essentially the relative orderliness that is found in the nature. Now, in order to utilize that, in order to extract the iron from the iron ore, in order to extract the manganese from the manganese ore, you need to spend energy. Now, the energy is also available as a negentropy stock. Energy is also available as a negentropy stock, in the sense, where is energy available? Energy is available in the oil fields, energy is available in the coal fields, coal mines, and the coal mines are essentially some place where there is a higher probability of finding carbon. That is the coal mine, right? Oil mine is out of the whole mass of disorderly material, there is some place where there is a higher probability of finding hydrocarbons. So, these are the oil mines. So, oil fields. So, we suck in that and use that. So, the energy resources are also negentropy stock. But the negentropy stock is not only the energy resources or the material resources, all together we have the negentropy stock, and the complication is because there are some which are material sense negentropy stock, there are some which are entropy sense negentropy stock. So, you first have to utilize the entropy, the negentropy stock related to the energy sources, produce utilizable energy, use that in order to extract the useful material. That means, when the steel is made, some time back it was an iron ore. From there, in order to extract it, you had to spend energy. In order to put it in the blast furnace, you have to spend energy. From the blast furnace to a whole cube of iron, you have to spend energy. In order to purify that into steel, you have to spend energy. And then in order to make this particular cylinder, you have to spend energy. So, the whole process contained various points at which you had to spend energy in order to get the final thing. So, the energy engineering is essentially consists of understanding this whole process, through which it came from the ore stage to the final product which is useful to man. And in order to produce the final product that is useful to man, you had to spend energy, and in order to do that, you had to locate the negentropy stocks, both the material negentropy stocks as well as the energy negentropy stocks. For the energy engineers, it is more meaningful to try to identify and understand the energy negentropy stocks. So, we will talk about that in this course. So, this is the essential grounding on which we will build up in the next few classes. But probably you are used to a different concept of entropy, right? Those who have done some course in thermodynamics are probably used to, or more used to, the concept that change in entropy is dq by t, right? Yes, this is the concept of the absolute entropy of a body, and the change in entropy that happens in a thermal process is represented by dq by t, where there is a heat transfer that is represented by dq by t. But remember, that is a very constrained concept, in the sense that if you have two cylinders and you remove the partition, one with oxygen, another with nitrogen, with the same temperature, there is no thermal process, there is no thermal mixing, yet you know now that there was an increase in entropy. What was dq? 0. So, change in entropy you cannot really visualize only in terms of dq by t, but yes, dq by t is the change in entropy whenever there is a heat transfer. Okay. Now, the moment you understand that, and the moment you understand the law of thermodynamics, that left to itself the entropy always increases, you can easily obtain, you can easily derive the maximum efficiency of a converter. You can do that. See, suppose you have something, the reason that the idea of the ship going through the sea, sucking in water and utilizing only the amount of heat obtainable by cooling it by just 1 degree, that did not work, was because in order to utilize that, you need to have a passage of heat from a source to a sink. Without having a sink, without having another temperature, you cannot have that. In fact, nowadays there are such converters which utilize the temperature difference between the top of the sea and the bottom of the sea. So, then that you can do, but simply by utilizing the water from the top of the sea at the same temperature, you cannot. So, you need one source at a temperature say T1 and another sink at a temperature say T2, and suppose there is a some kind of a converter. I am not talking about what converter it is, this one, which gives out a amount of mechanical power W, and we are asking what will be the efficiency of such a system. So, here is a body A, here is a body B. The amount of heat taken from the body A is Q1, which is at temperature T1, amount of heat that is discharged into body B is Q2. Okay? Fine. So, how much entropy is lost by this body? A is Q1 by T1, dq by T, how much heat went, that is Q1, at what temperature, T1, therefore Q1 by T1. Entropy gained by B is similarly Q2 by T2. Okay. So, Q1 by T1 and Q2 by T2. So, the whole system, how much is the change in entropy? Obviously, Q2 by T2 minus Q1 by T1. Okay. So, right, and that by the just stated law of thermodynamics should be positive, entropy always increases. Okay. This tells you what? Q2 by Q1 should be greater than, right? Fine. Now, how much is the efficiency of the system? The amount of energy output is W, amount of energy input is Q1. So, efficiency is and how much is your W? By the first law, it is nothing but Q1 minus Q2. So, this is sorry, this is nothing but 1 minus, right. Now, we have already seen that Q2 by Q1 is greater than T2 by T1, which means the efficiency is always less than, that is it. So, the moment you assume, you understand that entropy of a isolated system cannot decrease, it always must increase. Immediately for any anything that converts heat energy into mechanical energy, this must be the maximum amount of energy available. Okay. Okay, we will continue with this in the next class. Only let me tell you at this stage that this tells you that not the whole of a heat, even though the first law says that the energies are equivalent, you can convert one form of energy to another. But the second law says then that you cannot convert heat energy to electrical energy or mechanical energy at 100% efficiency. You must have two different temperatures, and the efficiency limit is this 1 minus T2 by T1. Okay. Remember, this T2 and T1 are absolute temperatures, not centigrade. These are absolute temperatures. For example, inside a power plant, what is the, is there a class after this? Probably. Okay, we'll come to that in the next class. There seems to be another class after this. Okay, so that's all for this class today. We'll reassemble tomorrow and continue with it. Thank you.